Hello and welcome to the solutions to sheet 5 of section 14 on polynomials. We're on the way to the Hilbert Basis Theorem. And what we're doing here is we have constructed in the previous sheets these AUX ideals. Given an ideal in the polynomial ring, we can construct many auxiliary ideals of the ring. And we proved that these things were monotone. We proved that if A was less than or equal to B, then the ath auxiliary ideal was a subset of the bth auxiliary ideal. So that means that when you take the union of all these things, union of ideals isn't in general an ideal, but if it's somehow an increasing union, then this is an ideal. And we should be able to prove this using, what would it be called? I guess set.mem. Mem union or something. Is that, yeah, there we go. Excellent. So set.mem union is going to get us through all of this, I think. So we've got to prove that 0 is in the union of these ideals. So we've got to prove that 0 is in one of the ideals. So we can use any of them, right? We'll use the 37th one. And now the why is 0 in that 37th ideal is because 0 is in every ideal. So what would that be called? Ideal.0 mem or something. No. Oh, maybe I have to say it's exact. I could call it this, and I could maybe give it exact. That'll maybe force lean to unify. Exact this. No, it didn't work. So maybe I'll tell it that the ideal we're looking for is this one. Yeah, now it's worked. There you go. It was definitionally equal, but we needed to persuade the unifier to take it seriously. And now what? Intros FG, HF and HG. So we know that F and G are in the union, and so we need to know that F plus G is in the union. So let's rewrite set.mem union at everywhere, AH, FHG in the goal. And then we can do cases, recases HF with AHA, and then recases HG with BHB there. And then, so the idea is that F is in at the 8th level and G is in at the Bth level, so we use max AB there. And why is F plus G in that? It's because the sum of two elements in that is in that. So apply, I might have the same problem. AUX ideal I max AB. Dot add mem, right? Yes. And now, and this one is because we're monotone. So refine. What was it called? AUX ideal dot mono or something. AUX ideal dot mono, and then it wants the ideal. No, it doesn't. It wants the inequality, and then it wants HA. Oh well. HA is supposed to be the inequality. Oh, did I get did I put them the other way around? No. Is it underscore HA? Oh, there we go. I've got to prove that A is, that would be called something like LE max left or something. LE max left. Now it's complaining because LE max left wants explicit inputs, so it's probably going to be AB. How did that work? Oh, so there we go. That's so this is exact this there, and the other one will be the same. This will be LE max right, and this will be HB. I would imagine, yes. So there's add mem, and now what? Small mem. Again, intros R and F and HF, and then we have to rewrite set.mem union at HF and the goal. And so now we can use the same I, right? Our cases HF with I. We can just do cases probably. Cases HF with IHI, and then use I. And now Y is this. This will be called refine ideal.smallmem. I wonder if I can do, no, yeah. I've never heard of ideal.smallmem. But ideal.mulmem, or is it submodule? Maybe we should use submodule.smallmem. What's he complaining about? Not enough underscores. It's honestly, it's exactly this. Trust me. Submodule.smallmem. What does it want? It wants the submodule, which I don't want to give it, and then the element of the ring, and then the prefix in. So this is F and then HI. How about that? No. Okay. So it still wants this. Oh, it still doesn't work. Oh, it's because I put F there. And it should be R. There you go. I wonder if it would have worked. So that was an error on my part. No, it still didn't work. So there's the proof of that. So this union of ideals is an ideal. When am I in the union of the ideals? So that will be, that's exactly ideal. Aha, so if I have to unfold Orcs ideal 2 as HJ or something. Yeah. And then desimp at HJ. Oh, it doesn't like it. What about simp at HJ? Does it ever? Yes. You see, that's the same thing, right? So this is simper using HJ or something. There. And now instead of unfolding it, we maybe could put it here. Yes, there we go. So there's a proof of that. And the if and only if. Actually, we might be able, there might be a trick here. We just might be able to do exact set dot mem union. Is it that? It is, yes. This is probably exact set dot mem union 1 or something. There's probably a way of doing this. HJ. Yeah, there we go. So there are, these are essentially term mode proofs, really, aren't they? That one's that, and that one is just this. So that will be useful for later. In fact, they might be useful for now. So here's the meat of this sheet. We're claiming. So this ideal. So in the situation, this is the first time where we assume that the ring is Noetherian. In the Noetherian situation, we're saying is that this infinite union of ideals must stabilize. And so the proof is this infinite. This Orcs ideal 2. This infinite union of ideals is finitely generated, and the finite generators will all. You should imagine that this is probably in the library already somewhere. The fact that an infinite sequence of this is completely off script, but I wonder if I can just prove. Is there some statement that an infinite sequence of ideals must stabilize? I don't see it immediately. It's going to be there somewhere. Right. I mean, it might be somewhere in his Noetherian. This wasn't really what I was planning on doing. I was just going to prove it. It suddenly occurred to me it might be there already. I mean, I don't see it immediately. Oh, you see, this is going to be this thing here about is well founded. It will somehow. Anyway, there is probably some way of doing it involving well founded. So question: can this be done with that? But rather than leap into this and make this video overly long, because I can quite believe I'll get stuck, I'll go with the proof I know I can pull off, and that is, let's get the generating set. So how would this work? Where's the generating set? So why don't I just do have : equals is an Noetherian ring if ideal is finally generated. So this thing here, it wants a ring, so I'll give it R, and it wants a proof that the ring is Noetherian, so I'll give it HR. Oh dear. Oh, it's an if and only if, so I'll put the dot one there, and now it's an implication, so now I can feed it HR. And now I know that the ideal is finally generated, so I can feed in aux ideal to I there, and now I know that this thing is finitely generated, and so I can probably do cases. I could probably do obtain, and this will be the finite generating set and a proof that it generates, I would imagine. Yeah. So that we've used the fact that this aux ideal to I, this union, is an ideal, so it has a finite generating set. And now I want to look at every single one of these elements of R, and the point is, we know we have this mem thing, this mem we've just proved above, that if I have an arbitrary element in I, so I should prove, what I need to do next is I need to prove that if you're in S, then you're in aux ideal 2, because then I'll be able to use mem. So have H S mem, I claim, so S, so now that R would be in R. For all R in R is in S, implies R is in aux ideal 2. That I think that's the second thing we need. So why is that true? That is just, I could rewrite HS there, and then intros RHR. And I might not, and now I have to apply ideal subset span or something. Yes, and now this is HR. Didn't like that. Exact HR. Why did it not like that? That's slightly surprising. If I don't do the HR here, does that work? So what's this apply doing? Refine ideal subset span underscore. Does that work? That does work. And then can I put HR here? There we go, that works. So this is exact this thing here, and so now you do wonder whether I can get rid of this HR. I can get rid of this HR, but I can't. How annoying. Okay, so that's why HS-mem is true. And so now I want to, what do I want to do? I want to use this mem. You see, this just says that everything in Orcs ideal, everything in Orcs ideal 2, there is an M, but I actually want to get the function that returns that M. So that would be the choose tactic, right? Choose mem I. Choose mem I. What's the R? Choose GHG using mem I. Try that. That looks good. Now this G is now a function. G is now a function that says you give me an element of R. If it's in the Orcs ideal, then I'll give you a natural number. And HG says, oh, that natural number, that's the level where J occurs. So that looks good to me. Can I persuade it not to use J? No, it doesn't look like I can. I'm not entirely sure that's what I want. I think this is probably fine. Wonderful. So now we've got this function. And you see, so given an element of S, we can prove that it's in Orcs ideal 2, and so we can get a natural number. So now we can define a function from S to natural numbers that sends an element to an ideal where it shows up, and then we take the sup of that set. So let's let N be the fin set sup of something. Is there a fin set sup? Let's just put a comma. Yes, that seems to have worked. N wants to eat a fin set, so it's going to be S. And now N wants to eat a map from R to the naturals. And that map will be lambda R if R is in Orcs ideal 2 I, then, so we need a name for that. If R is in Orcs ideal 2I, then the natural is G, it's GRHR. And if that's not true, then we don't care, because we're never going to actually run that. So now we have an error for the if R, so it doesn't know. So this is some stupid decidability error because it can't do the case split on the if. So let's just go into classical mode. And now this works. And now is N a natural yet? N is a natural. So we can in fact just, we don't need to define it, we can just use that. There. So it's the, it's going to take all the elements of S, evaluate this thing here. Well, all the elements of S are in Orcs ideal 2, so it will use G. And then it will take the sup of those things. So now what have we got to prove? Intros MHM. I've got to prove that, you see, this says if M is sufficiently large, then I claim that the full union is equal to the mth level. So the proof of that will be, I guess apply, we want to prove inclusions in each direction, right? So that will be called le.antisim or something, or le underscore, is it le underscore antisim? Yes. So now we've got to prove both directions. So the first one is the hard direction, and the second one is just the inclusion. We've got to prove that this is a union of these things, so we can just do intros XHX or intros RHR. Have we got any R's? No, that's okay. And now, have we got mem Orcs ideal 2 or something? Yeah, so we can rewrite mem if. And now we've got to prove that there exists an m such that it's at level m, and I'm just going to use the m we have. And this is an assumption. So that's the easy inclusion. And all we've got left is the hard inclusion. Okay, so let's go. So intros intros RHR. Now what are we going to do? We've got to prove So we know that this sup is, we know that the sup is less than or equal to something. So that tells us that everything we're evaluating on. Okay, so we need to use finset.sup.le or something. Rewrite finset, is that there? Sup.le, is that a thing? Yeah, if there, that's what we need. Rewrite that at hm. Now let's see what hm says. Yeah, now hm says something useful. You see, we've got... oh, this is not great. Origin orcs ideal too. We need to know that it's in the span. I think we've... Orcs ideal too. This is the span of something. We can rewrite HS. Before we start this, let's rewrite HS. Because I'd rather just be talking about the generators. So when is the span of a set a subset of a submodule? It's when, so this is rewrite ideal.span. No, it's probably submodule span subset. No, subset. Span LE if or something it'll be called. There it is. It's exactly that. Oh, it didn't work. Let's try ideal.spanLE. Is that a thing? That is a thing. Great. So now we've just got to prove the elements of S are in the subset, and this is good. So M is sufficiently large for this to work. So now we can intros HS and HS. Well, we've got a capital S, so let's call it R, and then HR capital S. And then we do this rewrite finset there, because now we can use this, you see, we can now specialize HM at R and HRS there. And now this is a dependent if then else. So is R in this orcs ideal or not? Well, R is in S, and you see HS mem says if we're in so it's true. So we can rewrite diff pos at HM, and now we have this extra, there it is, we have this extra goal that we can actually probably fill now. Where is it from? It's from HS mem, so let's put HS mem something something. Does that still work? Yes. And now I've got to prove that R is in S, and that's HRS, so that's probably the last one. HRS. So that's worked. So now I know that, so R is some random element of S, and this G thing here says the level at which it shows up, you know, orcs ideal IG is less than or equal to M. And we have HG. Oh, that's a bit annoying. We need a proof that it's in. We need this. We're going to have to use this twice otherwise. Let's say have HRI orcs, and it is just this thing here. There, we may as well just make a little lemma out of this. HR orcs, R is in that thing there. And so now we can use HR orcs here. And Oh, there we go. It's easier to read now as well. And now you see HG, we can specialize HG. The idea is that because this is true, HG will tell us that R is in Orcs ideal I, this guy here, and then we can use monotonicity to get this thing here. So we could apply, we could do it backwards, Orcs ideal dot mono, and then feed it the inequality. What was it called? HM. Didn't work. It wants to know the ideal. How about that? That's worked. And now, why is that going to be true? That's going to be true because of HG now. Apply HG. Oh, bingo. And it was all over rather quicker than I expected. And that and that seems to be the end of that proof. So there you go. Thanks a lot for watching. So there's only one video left in this section 14 series, and that's the proof of the Hilbert Basis Theorem.